Hi, I'm Dr. Ralph Rudd, and this is the Fundamentals of Finite Difference Methods in 10 minutes. I'm from the African Institute of Financial Markets and Risk Management, and this is a pop-up lecture that I recorded, or am recording, at the beginning of 2021. So let's dive right in. What we want to do is use finite difference methods to solve partial differential equations, or PDEs. PDEs are equations that describe dynamics. They describe how some quantity changes across both time and space. In financial applications, in mathematical finance, we want to price options by solving the option price PDEs that govern their dynamics. For instance, the famous Black-Scholes PDE. Let's take a look at what a complete finite difference solution to a PDE would look like. So, this is a pricing surface for a knockout double barrier call option. What you have is at the maturity time of the option, 1 year from today, you have the payoff of the call within the boundaries where the call hasn't knocked out. We use a finite difference method to propagate the PDE dynamics backwards through time from the terminal condition all the way until today, time 0. And what we end up with is the price of the option for different values of the underlying. That's usually what we want. We usually want to price an option today. But of course, with a finite difference method, as you see here, I get back out an entire pricing surface. So in financial applications, this is generally what we use finite difference methods for. However, before we jump into pricing options like this, we would start with the diffusion equation, or the heat equation. And the reason we start there is the diffusion or heat equation is incredibly well studied. It has some physical intuition. You can think about it as the rate at which heat diffuses through a medium. And you can actually transform the Black-Scholes PDE into this form. Now, the heat equation states, if we take U to be the quantity of interest, we say here that the rate that U changes over time is proportional to U's curvature in space. Right? And our space domain is going to be x between 0 and cap x, and our time is going to be run between 0 and cap t. Because we have a first order derivative in time, we need an initial condition, one initial condition, that's that guy over here. Because we have a second order derivative in space, we need two boundary conditions. One when x is 0, the lower boundary condition, and one when x is equal to cap x, the upper boundary condition. Now, what would be our first step in trying to solve this equation computationally? The first thing we'd have to do is discretize our domain. So that's what we do. We had this continuous domain, 0 cap x by 0 cap t, but we replace it or approximate it with a finite grid of values in the range x and in the range t. We're going to consider a uniform grid only in each dimension. So x goes 0, delta x, 2 delta x, all the way until we get to cap x. And t goes 0, delta t, 2 delta t, all the way until we get to cap t. So our delta x and our delta t are going to be determined by our largest value, cap x, divided by the number of steps we want to take, which I've called here cap n sub x. The same for delta t. We're going to have cap t divided by cap n sub t. Now, our approximate function, I'm going to indicate by uij. This is equal to our true function u evaluated at the points on our grid points, xi and tj. So this is the mesh function that we want to build computationally. So now we have the finite grid. What's our next step? Our next step is to approximate the derivatives. Now, let's consider as an example how we could approximate the derivative with respect to time at the point tj. So we want to know what's the rate of change of u here at the point tj. Now we know what a derivative is, right? It's the infinitesimal rate of change. But if we approximate it, instead of looking at an infinitesimally small delta t, we're going to look at a delta t that's a bit larger. One way we can make this approximation is by looking forward. This would be a forward difference approximation, where delta u becomes uj plus 1 over delta t, which is tj plus 1 minus tj. Although this is all quite intuitive, of course we can approximate the derivative in this way. If you want to prove that this is a valid approximation, as in derive it and determine the error term, you have to use Taylor's theorem. But we can't do that in 10 minutes. So you're going to have to take my word for it that you can do a forward difference approximation in this way. You can also go backwards to do a backwards difference approximation, and you can combine the two to do a central difference approximation. So let's replace our derivatives with our approximations. we'll use a forward difference derivative for our forward difference approximation for our derivative with respect to time, and we'll use what's called a symmetric central difference approximation for our second order derivative with respect to space. And we take these approximate derivatives, plug them back into our heat equation, and then we shuffle them around a little bit. And what we end up with is this equation at the bottom here. This equation says, if we read it explicitly, that our u value at our next time step is equal to a combination of our u values at our previous time step, multiplied here by f, which is the mesh Fourier number. The mesh Fourier number is just that constant alpha that we had times delta t over delta x squared. The mesh Fourier number is important for scheme stability, but we won't touch on that too much here. Another important thing about this equation is that it's explicit. I can determine the value of u at the next time step explicitly in terms of the values of u at the current time step. What does that mean? Well, let's take a look at an illustration. Here I've drawn 3 of the grid points, and you can see that to compute a value on the grid at the next time step, I would use 3 values of the grid at the current time step adjacent to that value in space. Now, with this formula we saw on the previous slide, and given that we know our initial and boundary conditions, we actually have everything we need to do a computational solution, an explicit finite difference method for the heat equation PDE. If it's not quite clear yet how that would look, well, it would look like this. This is our finite difference grid, or our mesh grid that we constructed. It has nodes running along the time direction, and it has nodes in the space direction. The nodes in gray are nodes that we do not need to compute because they are perfectly computed for us by our upper boundary condition, our lower boundary condition, and our initial condition. The nodes that we need to compute are simply functions of the known nodes. And what I can do now is I can propagate this equation through time until I arrive at the terminal time. Although this is very straightforward to understand and implement, explicit methods can suffer from stability issues. A stability issue simply means that at my first time step I make some small error because I'm making an approximation, but that error grows through time. And that's it. Your very first finite difference method for solving a partial differential equation. So we covered how to solve the one-dimensional diffusion equation using an explicit finite difference method. If you wanted to study a little bit further, you'd need to look at what are known as implicit methods, where we use a backwards difference approximation or a central difference approximation to compute our derivative. And you could look at things like the theta finite difference scheme, which is a weighting between implicit and explicit methods. In the description of this video, I have a brief learning guide, which is really what a class outline would look like if you were to take a course like this at a master's level in financial mathematics. And the last thing that I just want to say is I highly recommend the Finite Difference Computing with PDE's textbook, which is available for free online, and I've got the link in the description. Thank you very much.